So today we will discuss some very important theorems based on symmetric and skew symmetric matrix, right? So the first theorem is, for any square matrix A with real number entries, yes, you can see that for any, it should be a square matrix only, right? So for any square matrix A with the real number entries, A plus A transpose is a symmetric matrix and A minus A transpose is a skew symmetric matrix. All right. So basically the theorem is, we have to prove that A is any square matrix we have given with the real number entries, and we have to prove that A plus transpose of A, it will be a symmetric matrix, and A minus transpose of A, it will be a skew symmetric matrix. So let's start the proof. First, you can see that this is A plus A transpose, and we will let this matrix as in the one form, right? As you know that we have denoted matrix with the capital letter, so I'll denote A plus transpose of A with the capital B here. So we have to prove this one as a symmetric matrix. So our first step is, we will take transpose both sides. When we take transpose both sides, this will be B transpose and the right hand side will be A plus A transpose and the whole transpose, right? Now next step, left hand side remain as it is. As you know the properties of the transpose of the matrices, I have already written the property that we are using here. That is, you can see that A plus B whole transpose. Now in the place of B, we are having transpose of A. So according to the right hand side, this will be A transpose plus A transpose and the whole transpose, because at the place of B we are having A transpose here. And the next step is B transpose as it is, and here it will be A transpose plus, again we will use the next property, that is the transpose of A. When we do the transpose two times, it will be equal to that particular matrix, so that will be equal to A. All right, so you can see we are very close to the result. So the right hand side will be A plus A transpose, right? So what was this? As you know that we have already let this A plus A transpose as B. So from the equation 1 that I have mentioned here, the left hand side remain as it is, and this is B, right? And you know that what is the condition of symmetric matrix? When the transpose of the matrix is equal to that particular matrix, right? So you can say that A plus A transpose is a symmetric matrix. So this is the proof of the half theorem. Now similarly, we will prove A minus transpose of A is a skew symmetric. Now again we will let this A minus A transpose as another matrix, that is C, right? So now again we will do the same step, do the transpose both sides, and it will be C transpose is equal to A minus transpose of A and the whole transpose, right? Now again we will use the same property but in the subtraction. So it will be, when we apply the property here, it will be A transpose and the whole transpose, right? Because at the place of B we are having the transpose of A. So the next step, C transpose remain as it is, and A transpose minus, again we will use this property that we have already used in the first right in the above solution. So this is transpose of A minus, when we do the transpose two times, it will be equal to A, right? Now students, this one step, next step is C transpose is equal to, you can write it as by taking, if we are taking minus common from here, so this will be A minus A transpose, right? Because when we take minus common from here, the negative will become positive, right? And the positive will be negative inside the bracket. So it will be C transpose, C transpose, and what is this? We have already let A minus transpose of A as C. So from the equation 2, this is minus C, right? And as you know that the transpose of the matrix, when it is equal to the negative of that matrix, that is a skew symmetric matrix. All right. So this is a skew symmetric matrix. So we have already proved this theorem, that is A plus A transpose is a symmetric matrix and A minus A transpose is a skew symmetric matrix. All right. So let's move to the next theorem, that is any square matrix can be expressed as the sum of symmetric and a skew symmetric matrix. So this theorem is, you have to prove that any square matrix, like if I am saying that I am taking one square matrix, that is A, right? And now we have to express this A as the sum of symmetric and skew symmetric, right? So as we have already proved in the last theorem, that is we are having A plus A dash means A transpose, right, is a symmetric matrix. And similarly plus, because we have to express this as the sum of symmetric and skew symmetric, right? So this is A minus A transpose, right, that is skew symmetric. Now can we write this as this way? No, because this is not balanced, because when we open it, the transpose of A and the transpose of A will be cancelled because these are of opposite sign, right? But A plus A, that will be 2A. So if I'm writing here 1 by 2 and here also 1 by 2, and now you can see that when we solve this, this will be 1 by 2A plus 1 by 2A, that is A. Now this is balanced, right? Now students, as we have already proved, that is A plus transpose of A is a symmetric matrix. And now if I am using the property, that is if A plus A transpose is a symmetric matrix, and if we multiply this matrix with any scalar, right? So scalar remain as it is and the operation will apply only on the other matrix, right? So this will remain the symmetric as it is and the scalar remain as it is, that is 1 by 2. All right. So similarly for the skew symmetric matrix, that is A minus transpose of A. If I am multiplying this with any scalar, so scalar remain as it is and this will be a skew symmetric matrix. All right. So now we can say that these 1 by 2 A plus transpose of A is a symmetric matrix and 1 by 2 A minus transpose of A is a skew symmetric matrix, right? And we already expressed this square matrix as in the form of sum of symmetric and skew symmetric matrix. All right. So this was the second theorem. Now next is very important, that is this expression unique or not? Means we can express the sum of symmetric and skew symmetric in any other form or not. So let's move to the next result, that is uniqueness, right? So the result is every square matrix can be uniquely expressed, that you can see that I have highlighted it. So can be uniquely expressed as the sum of symmetric and skew symmetric matrix, right? So yes, this is unique, right? So we have to prove this now. Now as we have already let the square matrix, that is A, right? Now I am letting here the two matrix, that is R plus S, because we have to express the addition between symmetric and skew symmetric. Now I am letting R as a symmetric matrix and S as a skew symmetric matrix. All right. So let's move to the next step, do transpose both sides. So when we do the transpose both sides, it will be R plus S transpose, right students? So what is our symmetric matrix? What is a skew symmetric matrix? Now this is A transpose, and when you apply the property here, you know what is the property? That is A plus B, the whole transpose is equal to the individual transpose. So we will apply this property here. In the place of A, B, now we are having RS. So apply the property, that is R transpose plus S transpose. All right students. Now you can see the next step. That is, I am writing it again for you. That is R transpose will become R, but S transpose will become minus S. Is this, you're getting this step or not? Why? Because we have let R as a symmetric matrix and S as skew symmetric, right? Because R is symmetric and S is skew symmetric, right? So as you know that if R is symmetric, the transpose of R is equal to R, and if S is skew symmetric, so transpose of S will be minus S. All right, students. So now I am numbering this equation as 2 and the first equation, this one, as first, right? Because now we will solve these two equations simultaneously. Now the first equation is A is equal to R plus S, and the second equation is A transpose is equal to R minus S. Now add these two equations, so left hand side will become A plus transpose of A is equal to this, so I'm writing here the equation. The first equation was, yes, the first equation was A is equal to R plus S. Now I'm solving these two equations, right? This is first and this is second. Now this is easy for you. So this is when you add these both, left hand side plus left hand side, that is A plus A transpose is equal to R plus R, that is 2R, right? And plus S minus S, that will be cancelled. So this is, now we can find R from here, that is R is equal to 1 by 2 and A plus transpose of A, right? And the next is subtract 1 and 2. Now this is 1 and this is 2. Now we will subtract this. This will be A minus A transpose, that is A minus transpose of A is equal to, now when you subtract this, R minus R, that will be cancelled, S minus minus, that will be plus, so this will be 2S, right? So this is 2S, and we can find S from here, that is S is equal to 1 by 2 A minus A transpose. All right, now this is R and this is S, right? So now put these two equations in the equation number 1. So when we put it, A is equal to R plus S, first I will put the value of R from here, this one I will put in the place of R, right? And now I'll put the value of S. Now, yes, this one is the value of S. Now, yes, you can see that what is this? Yes, students, as we have already discussed about this, that this matrix, any square matrix, is equal to the sum of symmetric plus skew symmetric, and we have already proved that is this one is a unique term. We cannot express other than this. All right, so I hope you are getting all the theorems. So thank you so much.